So today we have another one of our own. Sarah obtained her PhD in petrology from the Magma and Volcanoes Laboratory at the University of Clermont-Auvergne in France in 2010. Her work focused on experimental characterization of melting behavior of mantle rocks. Following her PhD, she obtained postdoc positions at Caltech and Columbia. She then took a visiting assistant professor at UC Davis. In 2006, she received a research fellowship at Cardiff University in the UK. And afterwards, she joined the Department of Geology and Geophysics at the University of Utah in 2018. Combining geochemistry, experimental petrology, and thermodynamic modeling, her research group produces innovative tools to constrain the role of crustal recycling on the nature of the mantle source of magmas. And with that, I'll let Sarah give her talk, and let's hear about mantle melting and magma. Yes.
Okay, so thanks for being there. I want to start my talk by, and obviously it's never work on the first slide. Start my talk by actually acknowledging all the person I'm working with, starting with my group. So in alphabetical order, Emily, Will, Sarah, Autumn, Otto, Ashley, and JR. The work that I'm going to present today would not have been possible with the excellent student I have in my group. And I also want to acknowledge all the collaborators I have in the US, in Europe, and in China. And so the bulk of my research is basically focused on constraining the mantle heterogeneity. So we know that the mantle is heterogeneous because we have field evidence from xenoliths that are brought back to the surface to different rock types that we can see in ophiolite or in ultramassive massif. We also have indirect evidence of heterogeneity. For example, we know that thanks to the seismic tomography studies that we have the slab that is going back, subduction slab that is going back to the mantle. And I'm going to this kind of plot. I'm going to come back to this kind of plot later, but we can also see that from the geochemistry of the lava, showing that this kind of scatter basically cannot be explained by the melting of a heterogeneous mantle. And finally, the numerical model also are telling us that with time, the mantle should become progressively more heterogeneous. So today I am going to focus on two aspects of this heterogeneity, the nature and the length scale of the mantle heterogeneity. So why these two parameters in particular? Well, this is two schematics representations of the upper mantle. Very different one, with one showing very large mantle heterogeneity and another one that is much more complex with very small mantle heterogeneity. And the mantle I'm going to talk about today is what we call DMM for depleted mob mantle, or more broadly, basically, that's what we call the ambient mantle, which is the mantle that is far from any hotspot or subduction zones, basically. And so the idea is with time, if you have a convection process going on, basically, you should see your mantle becoming progressively more and more heterogeneous, and the scale of this heterogeneity should actually become smaller and smaller with time, basically. So you will go with something that I will actually refer as a Mondrian-like mantle with very large scale of heterogeneity to something like a Jackson Pollock-like mantle with very, very small heterogeneity. And so constraining the size of this heterogeneity is going to help a lot in constraining basically the timing of crystal recycling and convection processes. So I'm also interested in knowing the nature of the heterogeneity. When I say nature, I'm saying, do we only have like chemical heterogeneity, or do we also have lithological heterogeneity? Because this is also going to inform us about crystal time scale. But it's also important because if you have actually recycled material in your mantle source, which I'm going to refer for the rest of this talk to pyroxenite. When I talk about pyroxenite, I'm talking about recycled material in the mantle. And peridotite and pyroxenite do not have at all the same melting behavior. This has been shown experimentally numerous times. And so this is an illustration of what I'm going to say. You see a plot with the degree of melting as a function of the temperature at 1 GPa, and the recycled material is represented in blue, and the peridotite is represented in green like that. And what you can see is the pyroxenite are actually starting to start before the peridotite, and they also have a higher magmatic productivity. So basically, they'll melt earlier and faster. So even if you have a small proportion of recycled material or pyroxenite in your source, this could correspond to actually a significant contribution in the magma. Okay, the problem is we really do not have any access to samples coming from the mantle directly until last year. The deepest hole that we were actually able to drill in the at the spreading center was 2 kilometers in the crust. This year, actually, during the expedition 399, they drilled up to 1 kilometer of mantle rock, actually, directly. So this is an amazing scientific achievement. Unfortunately, most of these rocks are actually extremely weathered by seawater alteration, and seawater alteration will have as an effect to change both the mineralogy and the chemistry of the rocks, basically. So we do not have pristine samples coming from the mantle. So for that, instead, we need a proxy that is going to help us to understand what is at depth, because we do not have access to what is at depth. And so for that, for decades, we have been using the mid-ocean rich basalt, or MORBs, basically. First, because basically 85% of the magmatic production today is produced actually along this mid-ocean rich basalt. And also they cover basically most of the globe. And on top of that, mid-ocean rich basalt are in place on a very young oceanic crust by definition. And so they are not affected by processes like crustal contamination, stuff like that. And heavy radiogenic isotope in particular can provide a very crucial information about the nature of the mantle source. So this is a plot similar to what I showed before, where you have the neodymium isotopic composition as a function of the strontium isotopic compositions. And all these data points represent different mid-ocean rich basalts, basically. And the thing that is very powerful with the heavy radiogenic isotope is they do not fractionate during partial melting and crystallization. So what that means is what you see in the basalt directly reflect what are the composition in the source. So if you have actually different composition in the basalt, you must have different composition in the source. And so the way this is usually interpreted is it's interpreted usually as a mixing trend between two big end member, I would say, the depleted MORB mantle that is interpreted as the melting residue of peridotite, and an enriched end member, which is interpreted as recycled material at subduction zone. And so this way, the MORB is giving us directly a window into the into the Earth's interior. Okay, this is a representation of MORB composition, still with a isotopic composition in terms of strontium and neodymium, but this time I plotted the MORB composition as a function of the latitude for the North Atlantic Ocean only. And so what you can see is the isotopic composition of the MORB, as we just seen in the previous slide, is not constant. You have like big variation like that in both strontium and neodymium, okay? And so just as a reminder, if you have high isotopic ratio for strontium, you are enriched, so you are pointing toward recycling material. If you are low strontium isotopic ratio, you are depleted, so pointing towards the residue of partial melting. And that's the opposite actually for neodymium. And what you can see is actually these big variations kind of correlate with the location of the hotspot. Basically, the mid-ocean rich basalt composition are more enriched when they are close to the hotspot than when they are far from the hotspot. And so far from the hotspot, you will have high neodymium ratio and low strontium ratio, which would correspond to this ambient mantle I was referring to. And it's on the base of this large variation that people initially said, well, the variations that we see in the mid-ocean ridge along the spreading sector must mimic the variation of length scale of heterogeneity that we have in the mantle. So we will have length scale of heterogeneity of several hundreds of kilometers like that to explain this variation. The problem with using MOB as a proxy for mantle melting is, I told you, this is usually interpreted as a mixing trend. So MOB, by definitions, are the product of magma mixing. And magma mixing will result in basically blurring this mixing trend because technically you do not know where are these end members. The enriched end member might be here or it might be all over there. Same thing for the depleted end member. And there are also some studies that show actually that magma mixing can even affect the direction of this trend. So maybe your end member are actually along this trend over there, okay? So to really actually characterize the components that are in the mantle source, what we need is samples that did not experience a lot of mixing, ideally that did not experience mixing at all, but we are going to try to target samples that experience as little as mixing as possible. And for that, we have been using cumulate from the base of the oceanic crust, basically, because the cumulate from the base of the oceanic crust corresponds to the first product of crystallization from mid-ocean ridge, okay? So they are corresponding basically to the first liquid that are delivered to the crust. So hopefully they have actually experienced less mixing than the magma that arrive at the surface. And so that's what we did. And we selected actually samples that are on the depleted side of this big trend, so far from any hotspot, with low strontium isotopic composition and a high neodymium isotopic composition. So those samples were actually collected during the IODP expedition 304-305 in 2003. Okay, and so to look at the composition of these samples, we use actually a three-step method. The first thing we did is element map of the samples. So that's what is represented over there. So olivine are in black, and plagioclase are in shade of blue, and pyroxene are in green to red variations like that. And we were doing that to actually target the most primitive part of this mineral to make sure that we have access to really the first liquid that crystallizes. So this particular case, we will target the dark blue, basically, and the greenish crystals like that. And so we did that, and we also did trace element analysis on those grains to have an idea of how much strontium and neodymium is present in each grain, so we know how much material we need to collect. And so to collect them, we actually did micromilling on these samples. So this is XPL image of the samples after micromilling. And so this is a grain of clinopyroxene of maybe 1 or 2 millimeters. And so the black part corresponds to what we actually selected to do the analysis, okay? And so the last part is wet chemistry, extract strontium and neodymium and do TIMS analysis to obtain the strontium and the neodymium composition of these different grains. So this is a plot I showed you before with the MOB composition along the mid-Atlantic ridge. And the red arrow corresponds to basically the variations that you observe in MOB at this particular latitude. And this is the variations we obtain in our cumulates, basically. And so don't worry about the samples, etc. It doesn't really matter. What's important is basically the chemical variations that we obtain in our samples from the same location in the same drain hole is basically 7 times larger than the chemical variations that you observe in the MOB. So this is really a demonstration that the mantle is actually looking more like a Jackson-Pollock mantle with very small scale heterogeneity, basically. And these big variations that we see here are not actually representative of the variation of the length scale of the heterogeneity in the mantle. They are actually the result of magma mixing. Okay? And so we can actually solve for how much recycled material and which temperature do you need to actually reproduce these big variations like that. So for that, I use two different proxies. I use the isotopic composition of the mobs with the recycled material that is actually characterized with the isotopic variability that we saw in the minerals. And I use the elevation of the ridge because the elevation of the ridge is basically a proxy for crystal thickness. And so using the parameterization I developed to model the melting of a heterogeneous mantle with peridotite and pyroxenite, I actually exactly reproduce both of this curve and this curve by varying the temperature of the mantle between 1245 and 1367. So a little bit more than 100 degrees, which is not a lot, basically, and varying the fraction of recycled material in the source between 3.2 and 8.5%. Okay? So the take-home message of this first part is that the mantle source of MORB is actually way more heterogeneous than we thought previously, and also heterogeneous on a much smaller scale. However, I still don't know what is the nature of this recycled material. Isotope can actually provide a lot of information, as we can see, but they are not going to tell us if we have different type of rocks in the mantle or if we just have chemical variation in the mantle. Incompatible trace elements like REE has been extensively used in geochemistry, but those elements are particularly sensitive to the process of partial melting and crystallization. So they are going to give you good estimation about that, but they are not going to give you any information about the lithology. Major elements, the problem with the major elements is pyroxenite and peridotite tends to actually produce melt that are very similar in terms of major element composition. So if you are really extreme peridotite and extreme pyroxenite, you will be able to distinguish between these two, but for most of the lithologies, you won't be able to distinguish pyroxenite melt and peridotite melt on the base of the major element. So what I'm going to try to do is try to convince you that FRTs is actually the right way to go when you want to try to better constrain the nature of the mantle heterogeneity. So what are FRTs? FRTs are the first row position elements, so that those are the elements on the periodic table over there. And what is very interesting with these elements is, in contrary to the REE, for example, that are extremely incompatible, first, FRTs tends to be relatively neutral during the partial melting processes, which means that the FRTs that you see in your basalt mimic the FRTs that you have in your source. So that's the first thing. The second thing that is very important is, despite their very neutral behavior, their partition coefficient are very contrasted between the minerals that can be present in the mantle. So I'm giving you an example with 5 different minerals commonly present in the mantle: spinel, olivine, orthopyroxene, clinopyroxene, and garnet. Zinc tend to partition a lot into spinel, while manganese tend to partition a lot into garnet. Okay, so you will have contrasted partition behavior like that. Why is it important? Well, let's say you have a mantle source and you don't know if it's a pyroxenite or a peridotite, and you have a given manganese-zinc ratio in the source. If you have a peridotite, what's going to happen is the basalt you are going to produce is going to be elevated in manganese and low in zinc, because the zinc will want to stay in the mantle because there is a lot of olivine and spinel, while the manganese do not have any minerals to accommodate them, so it will go in the melt. If you have a pyroxenite source, on the contrary, the manganese wants to stay in the source because of the presence of a large amount of garnet and clinopyroxene, and the zinc wants to go in the melt, so you produce a low manganese, high zinc ratio in your melt. Okay, so we can test this theory by actually using 2 series of basalts that have very contrasted FRT ratio. So I use basalt from Samoa and basalt from Iceland, And you can see that I'm looking at the zinc-iron ratio and the manganese-iron ratio. The reason I'm dividing by iron is because these two series of basalt did not undergo the same degree of fractionation. So it's just to correct for the different degree of fractionation between these two series, okay? And so Samoa tends to be enriched in zinc-iron and depleted in manganese, while Iceland is enriched in manganese and depleted in iron. So the theory should predict that Samoa tends toward a source that is more pyroxenitic, and Iceland tends toward a source that is more peridotitic. Okay. The classical model that I have been using for many years and a lot of people are using is to do a forward model. So for that, you need to basically assume what is the mineralogy of my peridotite, what is the mineralogy of my pyroxenite, and what is the composition of these two lithologies, and try to solve for the amount of peridotite and pyroxenite. Okay, so that's what I did as a first test, and I use this peridotite and this pyroxenite. These two lithologies have been extensively used in the literature simply because they are extremely well characterized experimentally. So people have been doing that a lot, basically. If you do that, if you try to solve for the proportion of pyroxenite and peridotite in the source for these two series of basalt using the manganese-iron ratio, you find 67% of pyroxenite in the source of Samoa and 34% in the source of Iceland. So on a first order, it's consistent with what we expect at the beginning. The problem is if you try to do that with zinc iron, then you need more than 100% pyroxenite in your source for Samoa and less than 0% pyroxenite in the source of Iceland. And so the big issue with that is this assumption. You don't know actually what are the lithologies that are present in your mantle source. So what we did is we proposed actually a new approach of looking at that. And instead of solving for the pyroxenite and the peridotite directly, we first solved for the bulk mineralogy of the mantle. And so if you do that, you do not have to do any assumptions about the lithologies that are present in the mantle. You just need to know what is the FRT's ratio in your mantle source, and you can get that from the EarthChem database, for example. And so that's the result we got for the manganese-iron ratio for Samoa and Iceland. And so this is a ternary diagram. So garnet pyroxene on the top, proportion of olivine and spinel on the right, and proportion of OPX on the left and right, doesn't matter. And so on the first order, what you can see is, again, this is consistent with what we were saying before, which is the source of Iceland is more depleted in chenopyroxene and garnet than the source of Samoa. However, you have actually a significant overlap between the two series of data. And on top of that, for one single ratio, you cover a very, very large range of mineralogy. So this is not very useful. You don't actually constrain very well the mineralogy of the source. You can do the same exercise with zinc iron. You see the same kind of result with a scatter that is even larger for Iceland, but Samoa being still quite enriched in garnet and chenopyroxene. Where it's becoming interesting is when you actually combine these two ratios. And so when you combine this and you look at the solutions that only works for the two ratio combines, the mineralogy is much more restricted like that. And now we can actually, so if I look at the average, you can see that the source of Samoa is actually quite refractory. It's enriched in olivine and in garnet, so it corresponds to a relatively depleted lithology at high pressure, while Iceland is much more enriched in orthopyroxene, significantly less enriched in garnet, and more importantly, Iceland must contain a little bit of spinel to actually explain this composition. And so what we are actually suggesting is this type of approach could serve actually as a first step approach when we do modeling to estimate the proportion of recycled material in the source of the basalt. So in this particular case, I will not use the two same lithologies for Samoa and for Iceland. I will use something like a very rich garnet pyroxenite for Samoa, for the recycled material, Well, I will use a spinel Websterite for Iceland. And if I do that and I reproduce the same calculations I did before, now I can actually find consistent results between the two ratios with 64% of pyroxenite for Samoa and 49% of pyroxenite for Iceland. Okay. So the take-home message with that is FRTs can be extremely powerful at helping us to basically quantify and describe the nature of the Mantle heterogeneity, but for that you need to actually combine different ratios together. Okay, so what's next? Well, the first thing is we need more experimental data, because so far, basically, there are only 2 experimental studies that has been dedicated to the partial melting behavior of FRTs. On top of that, and I didn't plan for it, but my cats are named Spinel and Mica. And it turns out that Spinel and Mica are 2 phases that can be present in the mantle source of basalt, and they can significantly affect the melting behavior of FRTs. And there are actually only few experimental data about these 2 minerals. I also would like to overall encourage the scientific community to analyze FRTs more routinely, basically during laser session and probe sessions, because those elements are most of the time relatively easy to analyze. And there are some elements like nickel that is extremely challenging to study experimentally. So more data we'll have on natural samples about nickel, better it will be, because we will remove bias due to the obvious disequilibrium you can have in natural samples. Okay, so for the last part of this talk, what I want to do is spend some time actually going briefly over some of the projects that are currently going on in my group. And so the first one is what's happened next with this model. And so what I actually present you today, I called it a proof of concept, because it's based on a very simple model initially. We actually use a batch melting equations. We only use 2 FRT ratio, basically two FRT ratio. And we also, instead of actually looking at the whole basalt variability, we actually only look at the average composition of this basalt, and just trying to compare what is the average of this one versus the average of this one. So now we want to do a much more complex model that takes into account the basalt variability, different melting regime, and more FRTs ratio. And this is what Emily is doing actually currently in my group. So she has taken this proof of concept and she has developed a full model in MATLAB to take into account all these parameters. And she's actually applying that to samples that we collected during the IODP expedition 396 to constrain the causes for the excess magmatism during the emplacement of the North Atlantic provinces. So the North Atlantic province is represented red and purple on this map. And it's a period of very high magmatic activity. And during the expedition, we actually collected samples on the Boeing Plateau of Norway over there. And what's interesting is we actually drilled samples at different locations that corresponds to different steps during the rifting process. So for example, the site 1566 corresponded to the initiation of rifting, while the sites 1571 and 1572 corresponded to the peak of activity. And what Emily has shown is basically when you go from initiation of rifting to peak of activity, you have a sharp sharp change of the mineralogy of the source, and you increase actually the proportion of garnet and clinopyroxene in your source when you reach the peak of activity. In parallel, Emily and Autumn has been working with a modified version of MELPX actually to test systematically different physical parameters that can affect magmatic productivity. So they tested the lithospheric thickness, the melting regime, the fraction of pyroxenites, the composition of the pyroxenites, etc. And what is very interesting is when you consider an active upwelling, which is what we expect during the emplacement of the NAIP, you can only put a certain amount of pyroxenite in the mantle before the mantle actually starts to lose its buoyancy. So the cause of excess magmatism during the emplacement of the NAIP is actually unlikely to be due to the fact that you had pyroxenite in the mantle. So now the question that they need to address is, if the pyroxenite are not responsible for the peak of excess magmatic activity during the emplacement of the NAIP, why do we still observe basically an enrichment in garnet and chenopyroxene corresponding to this peak of magmatic activity? So still using the samples from the expedition, Ashley is working on a completely different subject, basically, but she's looking at one particular unit, which is represented here. That's a BSE image of her samples. And this is a dacitic flow that is extremely vesicular and contain a lot of different xenocrysts, including cordierite, garnet, graphite, quartz, feldspar, etc. And so this dacite was actually emplaced in the early Eocene sediments on the Boeing basin over there. And this is very important because actually there has been actually some studies that suggested that basaltic intrusion in sediments, basically during the PETM, might have actually triggered contact metamorphism and potentially melting of the sediments. And contact metamorphism and melting of the sediments can release a lot of methane in the atmosphere, methane being a much more powerful green gases in the atmosphere that could have contributed to the PETM. So the PETM is a global warming event that happens at the same time than the NAIP was in place, basically. So what she did is she did a lot of different, she used a combination of different techniques like thermodynamic modeling, geothermobarometry, and uranium lead analysis on the zircon to actually try to determine what is the origin of this particular unit. And what she found actually is this unit is actually probably more than 1 million years older than the PETM. So this unit is not actually directly related to the PETM, but this unit demonstrates that the continental crust 1 million years after the PETM was still present on the Boeing plateau. So this has a lot of important implications for people that try to actually do the tectonic reconstruction of the rifting processes during the opening of the North Atlantic Ocean. On my side, I have been trying to look if we can actually find evidence of change of mantle source with time in other geological contexts. And so this is an example from Hawaii. And what we did is we look at the olivine composition, the FRT composition of the concentration in the olivine from the period of magmatic activity between 1500 and 1820 to the eruption in 2018. And what we actually observed is when you look at the FRT concentrations, you can actually correlate that with an increase of the chenopyroxene fraction in the source. What's interesting is between this period of time and 2018, the type of volcanism on Hawaii actually changed by a lot from an explosive volcanism to an effusive volcanism. So what we are actually suggesting is the processes that are happening in the source can actually have a direct effect on the type of volcanism that you can see in the surface, at least in the case of Hawaii, because if you have a larger fraction of pyroxenite, of chenopyroxene, not pyroxene, of chenopyroxene in your source, what this will do is your source is going to melt more easily, so you will produce more melt. And we actually also see that in the composition of our basalt. From this period of time to 2018, we see a slight increase of the degree of melting in the composition of the basalt. And if you have more melt, you can actually develop a larger magma reservoir in your crust. And so this will actually help to switch from an explosive magmatism to a more diffusive, effusive magmatism, because you have more time for degassing when the magma is transported from the mantle to the surface. Another place we have been looking for evidence for change of mineralogy or change of source with time is with my colleague Rong Xiu from the Institute of Geochemistry in Guian in China. And we have been looking at intracontinental basalt that are found in West China over there. And what we have, and so to do that, what we did is we use a little bit of geothermobarometry and relatively novel techniques, which is using the non-traditional stable isotope zinc and iron to characterize these basalts. And so when we see that, the geothermometry is telling us that the inland basalt are formed actually at higher pressure than the coastal basalt, and also the inland basalt show higher zinc and iron isotopic compositions in comparison to the coastal basalt. However, the coastal basalt show a much more radiogenic, traditional, heavy isotope, radiogenic isotopic signature. And so the thing you need to know is zinc isotopes are actually extremely sensitive to the presence of marine carbonate in the source. And iron isotopes are actually can also be used as a tracer of lithology in the source. So the way we actually interpreted that is a change of the source during the magmatic process from the first basalts that were produced inland to the late basalts that were produced on the coast, by having first adiabatic decompression of a mantle that contain eclogites that are carbonated eclogites, basically, and then progressive assimilation of material coming from the subcontinental lithospheric mantle, likely as a result of edge-driven convection, basically. The next step for that is we are actually currently working on samples from Cape Verde and Hawaii. Comparing these two islands is going to be very interesting because both of them has been proposed as having their source rich in pyroxenites, but Hawaii is considered basically in comparison relatively depleted in volatiles, H2 and CO2, while Cape Verde is actually famous to have some of these islands have outcrops of carbonatite actually into that. So we should actually see a very strong decoupling between the iron and the zinc isotopic signature. So stay tuned. I don't have the basic. I'm actually still on my side looking at some samples from Cape Verde. I'm not looking at basalt this time. I'm looking at some magmatic cumulates actually. And these magmatic cumulates are very interesting because they have olivine that have all the geochemical signatures that you can think of the presence of interaction with the carbonatite. So I told you Cape Verde is known to have carbonatite in some of these islands, but those samples are actually coming from Santo Anto over there, and there is no carbonatite at all on those samples. So the way I'm actually interpreting this signature, it's not a signature of a carbonatite, it's a signature of a very intense CO2 flux that was local and that was produced by rapid decompressions, and so the rapid exsolution of the CO2 that was present in the basalt at the beginning. And this rapid and local CO2 flux results in a very high degree of oxidation of the magma. And this very high degree of oxidation of the magma can result actually in the precipitation of a lot of oxides like that, like ilmenite and titanomagnetite. What's interesting is a few years ago, still with my colleague Rong Xiu, we actually looked at samples from the Emetian provinces in China over there. So this large igneous provinces is known actually to be the host of extremely large oxide and sulfides deposits. And by looking at the magma composition at this time, we actually concluded that the magma source of the Emetian float basalt should be actually extremely oxidized. So it turns out that FRTs might not only be good tracer for the lithological heterogeneity of the mantle, but they can actually also help to identify potential deposits for ore and sulfides deposits and better understand how these ore and sulfides deposits are actually formed. And finally, I'm also looking at other, at other techniques to better define, to better understand what are the processes of magma transport in the mantle. So, for example, I have been using with my colleague Lynn and Kills from University of Nebraska the uranium series disequilibria. So this is the sketch of the first part of this talk, basically, and the main conclusion for the first part of this talk is we actually prove that we could have different melts that are actually delivered in the crust at the scale of a Lego brick, like that. So you need a phenomenon, you need a process that allows you to actually have magma transport without any mixing like that in the mantle before they arrive in the crust. And what we suggested in this paper is that the liquid from the recycled material and the liquid from the peridotite should actually evolve into disconnected, separated network. And actually, that's what the uranium series disequilibria comfort actually as a hypothesis, because to actually explain the range of compositional variations that we see in the morb like that, you need actually a mantle with different porosities, likely with having melts from the peridotite circulating mostly via porous flow, basically, while the melt from the recycling material or pyroxenite will be extracted through high permeability channels. Okay, so I'm early, but that's okay because I speak fast. But I'm just going to conclude with this slide. This is a list of the different techniques I'm currently using in my research to actually address 3 different big thematics: the nature and the length scale of the mantle heterogeneity, the emplacements of large igneous provinces, and the processes of magma transport with potentially implications on the formation of ore deposits. And I just want to do one last acknowledgement to my colleague here at the U and elsewhere. And I will stop here if you have any questions.